So we were talking about uniform electric fields. We'd already spoken about electric fields generally, and then here we're talking about uniform electric fields. Uniform in any field means, as you can see over here, the idea of a uniform field means that it has a constant direction and magnitude. And so the way that we get uniform electric fields in a practical sense is when we have parallel charged plates. So in the case that you will often see in VCE exams, we have these two plates that are separated by some distance d, and we get an electric field between the plates because of a separation of concentrated charge. So we have one plate that has a concentration of negative charge, and we have another plate that has a concentration of positive charge, and because of those two separated charge concentrations, we get this electric field, meaning if we were to put a charge in this space, it would experience a force. If we put a positive charge in this space, then it would experience a force upwards, because it would be repelled from the positive charge on the bottom of the plate up to the negative charge on the top of the plate. I might actually use blue for that positive because that was the convention we were using last time. So we use negative, let's say red. Negative charge could be red, and a positive charge might be blue. And so a positive charge would experience a force upwards, repelling from the positive plate and attracted to the negative plate, and the negative charge would experience a force in the opposite direction. We spoke about the fact that we can describe that difference in charge concentration according to a voltage difference. So often the way this is practically done is we simply have a power supply that creates a voltage difference and connect that power supply to the two parallel charged plates. And what a voltage difference really is just a way of describing this separation of concentrated charge. However, this is what we're so that's really all stuff that we did last lesson. And similarly, just to recap here, we were talking about the fact that electric fields are often measured in newtons per coulomb, which is to say force per unit charge, but we can also describe it as volts per meter, which comes about from the fact that the greater the voltage difference that we have here, and the smaller the distance, so we can see from this equation, the greater the voltage difference and the smaller the distance between the plates, the greater the electric field. So based on this equation, we could also say the units are volts per meter. Now, back probably in year 11 when you were learning about electric circuits, you also would have learnt that voltage is a measure of the amount of energy that each charge has. So this is consistent with the way we've been talking about it, but just kind of two different ways of understanding what voltage is. So again, let's think about a charge concentration. So say we have a bunch of positive charges together, and then say actually, let's just leave it at that for now. So if we have that charge concentration, what do positive charges, they're all positive, what do they want to do? Well, they push against each other with a repulsive force, so they want to push apart. Now, because of the fact that they experience this force wanting to push them apart, if we force them into this kind of confined space, if we concentrate them like this, so they're all packed together here, then we have an electric potential energy, which is quite similar or analogous to a spring potential energy. If we compress a spring together, we know that that spring has a force wanting to restore it to its original length. So it has spring potential energy because the spring has the potential to kind of burst apart. And in the same way, when we concentrate these charges together, they have potential energy to want to burst apart from each other in a similar way. And same deal if we had a bunch of negative charges concentrated together. So just like we were saying up here, the voltage causes a charge concentration on the two plates, negative and positive. It also is a measure of, or really the way we quantify that charge concentration. So not so much also, but what that is equivalent to is measuring how much energy is stored per charge as we compress them together. And so this is how you quite likely would have learnt what voltage was in year 11, the idea that it's a measure of energy per charge, so that's joules per coulomb. So based on that, we can kind of rearrange this equation and say that energy is charge times voltage, QV. Okay, so what does that lead us to? This is really just saying the same thing. Potential energy is, I'm struggling as always with the highlight tool. All right, you'll just have to imagine the equal sign is highlighted there. Okay, so if we have some charge, so let's go back up to our plate here. Imagine that we put this negative charge that we had, imagine that we had it next to that negative plate. As we said, that negative charge will experience a force, a repulsive force from all of this concentrated negative charge on that plate, and an attractive force to the concentrated positive charge on the bottom plate. So there's a force clearly pushing it downwards. Now, because of that force, it, in this current position, has a bunch of potential energy. So it has that potential to move or accelerate towards the positive plate. And the way that we can measure how much that potential energy is by using the formula that we were just talking about here, Q times V. So the potential energy that that electron would have, or that negative charge, whatever it is, next to the negative plate, the potential energy it has would be measured by Q times V, where the Q is the Q of that individual charge. So however much negative charge this individual charge has. So if that's an electron, for example, then that would be the charge on an electron, which is negative 1.6 times 10 to the negative 19 coulombs. But it may not be an electron, just whatever negative charge it is. But we should state that it does need to be measured in coulombs for this equation to work correctly. And then the voltage would be the voltage between the two plates. So that's this voltage difference that we're talking about between those two plates. So here's the Q, and then this V, Q times V will give us the potential energy that that electric charge has. Now, that's in that position, very similar to if you hold a ball up at some height, we can calculate the gravitational potential energy due to the mass, which is kind of the analog or the equivalent to the charge in the case we're talking about, and multiplied by GH, so that is the gravitational field strength and the height. So those things will determine how much gravitational potential energy some ball or some object that we're holding has at a certain height. In the same way, Q times V in this situation gives us the electric potential energy that that charge has at that position. If we release a ball, then we know it falls and that energy turns to kinetic energy. And so once it hits the ground, all of that gravitational potential energy has turned to kinetic energy. In a similar way, if we release this charge and allow it to be attracted to the positive plate, then by the time it reaches the positive plate, all of that electric potential energy will have turned into kinetic energy. So we can think of this, so we've got our potential energy at this point, and now what we're saying here is that if we allow it to move, that potential energy will convert to kinetic energy. Again, struggling with the highlight tool, but you guys know what I'm doing. So up here, these equations look very similar, and they are, but just to try to help you understand what the difference is, up the top we're saying this is what the electric potential energy is. So often we use a capital U to represent any form of potential energy, and then the subscript E is telling us it's electric potential energy. So this is our electric potential energy at this point. The delta here, the triangle symbol delta, is telling us the change in. So this is saying the change in electric potential energy must be equal to the change in kinetic energy. So however much electric potential energy is lost is the amount of kinetic energy that is gained. Really we're talking about magnitudes here because one is decreasing and one is increasing, but the magnitudes are the same. And if we are allowing it to go that whole distance, then that change is equal to all of the electric potential energy that we started with, which is QV. So if when I say all of that distance, what I mean is, of course, if we started with the electron only halfway along, then we're not giving it, it doesn't have the same amount of electric potential energy at that point as it would up at the very top. So it's not actually accelerating through the entire voltage difference between the two plates. So therefore, we wouldn't be getting all of that QV turning into kinetic energy. But you will, in general, have problems where it does travel the whole distance between the two plates. And so we can say in those cases that the change in kinetic energy is equal to all of that potential energy, which is QV. Okay, so we've kind of got, now we've got this far, based on so that's just the equation we have above already. That is work done. So remember, we've spoken about what work means in physics. Work in physics means any change in energy. And a change in energy will occur when a force is applied to cause something to move a distance. So work done, change in energy, equivalent terms. So in any situation where you know that energy is changing through a transformation or a transfer from one thing to another, work is being done. And so then we can equate that work done to the force and the distance that's being applied in that. So again, if we look up here, it's moving through this distance d, the distance between the two plates, and the force is the electric force. And we spoke in last week's lesson about the electric force, but that electric force is equal to Q times E. So where are we here? So electric field strength is equal to force per charge. And if we just rearrange that, we can say the electric force is equal to electric field, sorry, I'll just do it in the other order, Q times E. So the electric force is equal to the charge multiplied by the electric field strength. So returning to our equation here, we've already established this bit. That's the same as the highlighted equation above. That is equal to work done just because of the fact that we have changes in energy. Changes in energy always mean work is done. When we have work done, we have a force that is being applied to push something through some distance. So force times distance is work done. And in the case of the electric force, that force F is equal to QE. So we can say it's equal to QED. Okay. And then here we kind of have, separately, I suppose, we have combined the two ideas. So electric field strength equal to voltage divided by distance. This is what we started with at the top. I might just remind you, because we kind of spoke about this last lesson, but this is really important. This part, I'm just going to use a different color to highlight. This part, which was the part at the top of this section, only applies for uniform electric fields. We would, to kind of have the equivalent for non-uniform fields, we need to use calculus, which is not relevant or not part of the course for VCE physics. This part, however, is true for all fields. So this statement that V divided by D is equal to F divided by Q is really true only in the case where we're dealing with uniform electric fields. But you won't have, in VCE, you won't need to deal with voltage when you're talking about non-uniform fields, separate to circuits, I mean. So when we're dealing with charges and electric fields, you will only be dealing with voltage in the case of uniform fields. You would not be dealing with voltage for problems that look like this, where we have non-uniform electric fields. Okay. Now, one thing that we will add to this that we've kind of alluded to before, but just to make it very explicit here, because of the fact that we're saying QED or QV here is equal to the change in kinetic energy, we can also have another equation which often proves useful, which is that half mv squared, which of course is the formula for kinetic energy, equals QV. Now, be really careful here for a couple of reasons. First of all, we've got two V's, but they're different V's. So this is capital V, which is for the voltage, and this is a lowercase v, which is for the speed. And again, just be mindful, this equation only applies in uniform electric fields. And it only applies when the charge moves through the entire voltage. So again, this would be a way of figuring out, calculating the speed when this negative charge finally reached this point. Then that would give us the speed. But and so it needs to be released from rest. If it already has kinetic energy when it leaves that point, then that equation won't apply anymore. So this is telling us how much kinetic energy it will gain as it moves through that voltage. But if it doesn't move through that entire voltage, or it already has kinetic energy at some point when it's released or whatever, then this equation won't apply anymore. However, VCE tend to be pretty reliable in the way that the questions you are given are applicable to this equation. And you will find this equation, or a very similar one, is on the VCAR formula sheet that you would get in the exam. Okay, so let's have a go at question 3. Of course, if you want to have a go at it yourself before me doing it, then you can pause it and do whatever you like. I'm going to jump straight into it. So, how much work is done on the electron by accelerating it from one plate to the other? So we've got, as always, I think it can be useful to kind of draw the setup that we have. So we have this situation, and the electron is accelerated from one plate to the other. The chances are it will, when we're doing that, it's going to be accelerating from the negative plate to the positive plate. It would kind of have to be a deceleration if it were going in the other direction. So let's assume that that's what's happening. So we have a negative electron here, and it is going to accelerate like that. And so we need to calculate the work done. Well, there's kind of a few different equations we could use here. So we could say force times distance, but that's not super helpful for us at the moment because we don't know the distance between the two plates. We also know that we have QED because force is QE, but we still don't know D, so none of these are really particularly helpful at the moment. But the other one that we know for uniform electric fields is QV. And so we know that because ED is the same as voltage when we're talking about a uniform electric field. So in this case, we don't need to know the distance to be able to calculate the work. So the Q is the charge of the particle that we've put in here, and in this case it's an electron. So we have 1.6 times 10 to the negative 19 coulombs, and V is 20 volts. So we multiply these two things and we will get 3.2 times 10 to the negative 18 joules. Now, I might point out here, so the charge on an electron really, of course, is a negative charge. When we're asked for the work done, however, we know that work is being done on the electron to give it more energy because it's accelerating from the negative plate to the positive plate. So you can choose how you prefer to think about this. You can think about it as, well, we know we're dealing with a magnitude thing here. So work being energy doesn't have a direction. It can increase or decrease, so we can get plus or minus, but we know it should be increasing in energy because of the situation. So we can then just deal with all the positive numbers here. So positive 1.6, positive 20. If you like, you could think about it as a negative charge, which is going through a negative potential difference because it's going from the negative plate to the positive plate, which is kind of going against the electric field direction. So I'll just go up to here. Remember here, we would normally have the electric field. Notice that the way I've done this, which is probably annoying with hindsight, but in this example diagram, the negative plate is on top and the positive is on the bottom. But just notice that the electric field goes from positive to negative. So in the case we have here, I'll draw what the electric field would look like. It would be going downwards the other way, from positive to negative. And so because the electron is going against that electric field, it's like it's working against the potential difference. So if you preferred, you could think about it as both a negative charge and a negative potential difference, and then you come out with the same answer there.